Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this lecture, we're continuing with our examination of electrophilic aromatic substitution. We want to look now at the third substitution. What happens to a benzene ring that already has two substituents on it? The following rules will cover the majority of the cases. Rule number 1. If two substituents direct an incoming group to the same position, that is where substitution occurs. That is where substitution occurs. For example, suppose I have para-nitrotoluene. So we have a CH3 here and NO2 here. Para-nitrotoluene, what kind of director is the methyl? What kind of director is the methyl group? Methyl directs orthopara. Now you can't substitute for a nitro group. Nitro is already occupying the para position. In electrophilic aromatic substitution, the leaving group is hydrogen. There is no hydrogen in the para substitution, in the para position, so we cannot do para substitution. That means the methyl is just left to direct ortho. So it's directing here or here. Now, what kind of director is nitro? Well, nitro directs meta, and meta to the nitro is these positions, the exact same position as the methyl is directing. So directing to either of these positions will produce the same molecule. Therefore, if we react this molecule, say with a Br2, What does Br2FeBr3 put on the ring? Well, if you said bromine, that's correct. So here's my methyl. Here's my nitro. And in the ortho position, I put Br. A bromine. Rule number 2. If two substituents conflict in their directive effects, if two substituents conflict in their directive effects, the two substituents conflict in the directive effects, the more powerful activator determines the site of substitution. Okay, determines the site of substitution. Now, consider the following molecule. Suppose I had parachlorophenol. What kind of director is chloro? Well, chloro is an ortho-para director, but you have an OH in the para position, so you can't substitute for that. That means the chloro is directing here or here. Where is the OH directing? OH is also an ortho-para director. It can't substitute para because there's a chloro, so it can substitute ortho to the OH. OH is directing to either of the red positions. Chloro is directing to either of the black positions. There is a conflict. Where does substitution occur? Well, if we react with Cl2, AlCl3, just like in monobromination, of a unsubstitute benzene, this will put which puts bromine on, AlCl3 and Cl2 will put a chlorine on the ring. Now, where does the substitution take place? Cl is a mild deactivator. OH is a very strong activator. OH, according to Rule 2, wins. Which means substitution will occur ortho to the OH. And there you have it. Rule number 3. If two substituents are deactivators, a third substitution, and remember that's a third electrophilic substitution, a third, let's put that in, electrophilic substitution third electrophilic substitution is usually too difficult. Too difficult to carry out. For example, suppose I have metanitro benzene. Both groups are meta-directors. Both groups are directing to the same position here. If you hit this with HNO3 and H2SO4 and try to put on a third nitro group, you will get no reaction. And the reason is the two NO2 groups withdraw so much electron density from the ring that the electrophile nitronium ion, NO2+, just can't attack. It's interesting, therefore, that you typically don't hear of TNB. TNB being trinitrobenzene. But you have heard of the molecule TNT. In trinitrotoluene, you have an activator, the methyl, which allowed placing 3 nitro groups around the ring. So it's very difficult to make trinitrobenzene. You'd have to make it from some alternative route. And being that these molecules are explosive, it would be difficult to make. TNT, on the other hand, has the activating methyl group, which allows the placement of more deactivators on the ring. Okay, so 2 deactivators on the ring usually kill electrophilic substitution, making it too difficult for it to occur. Lastly, rule number 4. If two substituents are meta, substitution between them does not occur. The reason for this is presumably due to steric effects. Okay, so let's pretend I have, or let's assume I have, metachloroanisole. Let's consider what kind of directors we have. Start with the chlorine. The chlorine, what kind of director is it? The chlorine directs orthopera. So the chlorine is directing here, here, and here. What kind of director is the OCH3? The OCH3 is an orthopera. An ortho to the methoxy is here, and para to it is here. So the two groups, chloro and methoxy, are directing to the same position. Now, suppose I react this with Cl2AlCl3, which will put a chlorine on the ring. Potentially, there are 3 possible products. We could put a Cl para to the OCH3. The next possible product, of course, is ortho to the CH3, OCH3, but para to the Cl. The last possibility would be between the chloro and the methoxy. Now what's interesting about this, Rule 4 stipulates that substitution in this position, right here, in between the methoxy and the chloro, does not occur because of steric effects. That would not form. In fact, if we examine the percentage, and you're not required to know these percentages, we get 64% para to methoxy and 18% para to the chloro. Presumably the differences in percentages may be attributable to steric effects. So metachloroanisole yields 64% 3,4-dichloroanisole and 18%, 1, 2, 3, 4, 5, 2,5 dichloro. Anisole. Okay. With these four rules, we pretty much can handle all of the cases that come up in the third substitution. You effectively can carry out the third substitution. Now, we have examined electrophilic aromatic substitution. We've looked at substitution of a benzene, we've looked at the second substitution and the third substitution. All of this chemistry has focused on the aromatic ring itself. What we're going to do now is move from the aromatic ring and examine the influence the aromatic ring has on substituents. Now, some of this chemistry we've already had. For example, we have learned that the benzylic position of a carbon is especially stable for carbocations. That in benzylic carbocations, for example, even if the carbon's secondary, you will not want to shift to a tertiary because the benzylic carbocations resonance stabilize. And we've learned that these benzylic positions are especially stable due to the influence of the aromatic ring. And we've learned in this course to draw resonance structures for carbocations, for example. Here is the benzylic carbocation. And we can draw resonance structures that move this positive charge around the ring. And we move the pi electrons towards the positive charge. Turns out the aromatic ring doesn't just stabilize the carbocation. It can also stabilize the radical in much the same way. Now when moving one electron, we use fish hooks. Single-headed arrows. And so you have a resonance stabilized radical. Just like the aromatic can stabilize a carbocation or radical, the aromatic ring can also stabilize the carbanion. When there's a lone pair on the CH2. In this case, the lone pair moves away from the negative charge. Full-headed arrows move electron pairs. There we go. So a carbanion is also equally resonance stabilized. And in fact, it doesn't have to be carbon. For example, we learned that phenol is more acidic than regular alcohols when we studied alcohols. Phenol could readily deprotonate, giving you phenoxide. Why? Because just like the benzylic carbanion, I can draw the exact same resonance structures for phenoxide as I did for the benzylic carbanion. They're exactly the same. The only difference is you have oxygen, which has a few more lone pairs. And there you have it. These bottom two carbanions are exactly the same. The only difference in the resonance structures is one is an oxygen for the phenoxide anion and one is a CH2 for the benzylic carbanion. So what this shows is that the aromatic ring can directly influence the chemistry of the carbon or any atom directly attached to it. Well, how does this affect chemistry? Well, some of this chemistry we have seen, some we haven't. A new piece of chemistry caused by the influence of the aromatic ring on the atoms attached to it is what happens if you oxidize an aromatic that has an alkyl. As long as the alkyl has a benzylic carbon with an H. So it can have a methyl, it can have an ethyl, we can even have an isopropyl. If you take any of these, react them first with one reagent and then secondly with another reagent. I'm not going to use one or two. You may that makes you think we're doing it in two separate steps. No, we're not. We're going to use reagent A and reagent B all together all at once. Okay? So you have A and B. A and B. What is A and B? A, compound A, is hot KMnO4. So KMnO4 and heat. Reagent B is acid, H3O+, so just H+. Hot KMnO4 and acid. And if you react this, you will make benzoic acid. What's really interesting about this reaction is that you have to have a benzylic hydrogen. If you have a tert-butyl benzene and you try this reaction and you have 3 methyls off of the benzylic carbon, you will not produce benzoic acid. You will not produce the benzoic acid because the benzylic carbon lacks the hydrogen. Now, this can be interesting when you get very complicated molecules. For example, I could give you something like this. And you look at this and you say, oh my. So KMNO4, acid, and heat. I hit this with hot KMNO4, and you look at this and say, what possibly happens? What you have to do is check the benzylic carbons. Well, there's a benzylic carbon here, there's a benzylic carbon here, and there's benzylic carbon here. Do they have H's? Well, there's two H's here in this line formula. There's two H's here. And this has 3 bonds, so that means there's 1 H. So all the benzylic carbons have H's. Therefore, all of the benzylic carbons become CO2H groups. And the product of this reaction is this. Now this is very different from what we saw in alkenes. You must keep the chemistry we studied in alkenes separate from this. Aromatics react differently. Remember what happens in hot KMNO4 with alkenes? Let's try this. Suppose I give you 1, 2, 3, 4, 1,4-cyclohexene. So a 1, 2, 3, 3,6-dimethyl 1,4-cyclohexene. I give you this molecule. This is a diene. It is not an aromatic ring. Hot KMNO4 H plus and acid. Heat. You split the double bond. And you put double bond O's. Where there was a double bond, you put double bond O's. Off of the double bonds, if there were any H's, and there were, they become OH's. So you get 2 molecules of this. You could write it this way. Two of these guys. The top is just line formula. The bottom is more condensed structural formula. Either way of writing it is fine. Alkenes rupture the bonds. What if you were given paraxylene? Most common mistake students make is they treat the aromatic ring as if it was an alkene. And they start putting double bond O's between the double bonds of the aromatic ring. But that doesn't happen. Aromatic rings are stable. They have a special enhanced stability because of the conjugated pi system, the aromatic ring system. And so the double bonds don't rupture at all. KMNO4 acid and heat causes reaction at the benzylic carbons. And you end up producing (1,4) benzene dicarboxylic acid. And the double bonds are intact. So keep the reaction straight. Make sure you understand what is going on. Now, turns out phenol actually has a very rich, diverse chemistry. This is the OH group attached to the aromatic ring. As we've already indicated, the phenol molecule is more acidic than a regular alcohol. And the reason for this is resonance stabilization of the phenoxide anion. So where most alcohols don't react significantly with hydroxide, phenol can readily be deprotonated and converted to the phenoxide anion. Now, the phenoxide anion can be used to react with a molecule like Rx to do substitution reactions and produce ethers. This was the Williamson synthesis of ethers. And this chemistry is made easier. Hydroxide is able to deprotonate phenol directly as a consequence of the presence of the aromatic ring. Phenol chemistry is very rich. We can react phenol with carboxylic acids. We learned in the alcohol section that if you take a phenol or any alcohol in equilibrium, the presence of acid, you will lose water and produce phenylethanoate, an ester. Now this is an equilibrium and the yields are not great, but you can shift the equilibrium to the right by driving off water. However, you can actually prepare a reagent that will give better yields of the ester by taking two carboxylic acids, reacting them together and dehydrating them. If you take two carboxylic acids together, react them, and of course this is also reversible, you can isolate a molecule called acetic anhydride from acetic acid. Acetic anhydride essentially is a pair of carboxylic acids that have kicked out water. Now, if you isolate acetic anhydride, you can store it and you can use it as a reagent. If you react acetic anhydride with phenol, you can make better yields of the ester. Put phenol over this arrow. The way this reaction works is phenol actually attacks the carbonyl. There's a delta plus on the carbon from the electronegative oxygens, and you will produce this intermediate, very short-lived, negative charge on the oxygen, and we have this very good leaving group, O, C double bond O, CH3. The acetate anion is a weak base, and so is kicked out very well. Now the pi bond reforms, and you kick out acetate. And you get CH3, C double bond O, O, phenol, still has the H on it, so still a positive charge here. And you get plus, leaving group O minus. Now this is a very weak base, but the protonated ester is very acidic, so it can lose the proton to this acetate unit and give us the ester. There we go. Where this guy just grabs the proton. Now this type of chemistry with acetic acid, and the fact that there is a direct influence of both the phenol on the oxygen and the oxygen on the aromatic ring, leads to two very important reactions that we want to look at now. One is called the Kolbe reaction, and it is a synthesis for acetylsalicylic acid. You are responsible for the Kolbe reaction. Now the Kolbe reaction involves deprotonated phenol. So we utilize phenoxide in the Kolbe reaction. So I'm going to have an O minus here. Some pi bonds. Now I'm going to react this with C double bond O. Sub C double bond O. Carbon dioxide. Carbon dioxide is a very stable molecule. It is susceptible to nucleophilic attack. However, it's not a very powerful electrophile. So why would carbon dioxide react with an aromatic ring? Well, phenol is near the top of our activators for electrophilic substitution. Deprotonated, an O minus becomes even a more powerful activator than the NH2 of aniline. This would be at the top of our list of activators, representing one of the most activated aromatic rings. As a result, this ring is so activated, so electron-rich, that it can be attacked by even weak electrophiles like carbon dioxide. The oxygen can temporarily dump in a pair of electrons, and the pi electrons can attack the delta plus on carbon. One set of pi electrons have to move out to the oxygen, otherwise we'd have too many electrons. What do we have when we're done this? Well, now we have a double bond O. We have a pi bond here, a pi bond here. We still have our H. And we have a C double bond O. O minus. Now we've disrupted aromaticity, and this intermediate that forms is very short-lived, and quickly the pi electrons shift grab the H, electrons move from the bond, and oxygen ends up grabbing the H and restoring aromaticity. And we produce an OH restore our pi bond, our aromatic ring is restored, and we have C double bond O, O minus. Okay. Now if you hit this with acid, at this point, you will protonate and make salicylic acid. You'll protonate the O minus, CO2 minus. This molecule, salicylic acid. Salicylic acid is known to be a painkiller, but it's a bit harsh on the stomach. And to reduce its reactivity, it can be reacted now with acetic anhydride. We had just seen in the previous reaction that acetic anhydride with phenol makes ester. And so this will have a CO2H, we'll have an oxygen, C double bond O, CH3, ester form. And this is acetyl, salicylic, acid. Labeled from the A, the S, and the A. Its brand name is called ASA, and it's marketed and sold as aspirin. Billions of dollars of sales of aspirin each year. This is the Kolbe reaction for the synthesis of aspirin, and you are required to know it. All right, let's look at another reaction of phenol and see if we can sort out what's going on. This reaction is called the Reimer-Tieman reaction. The Reimer-Tieman reaction. In the Reimer-Tieman reaction, we take phenol we react it first with CHCl3, hydroxide, at 70 degrees C. And then in step 2, we add acid, H3O+. What do we produce? we produce this molecule, an aldehyde with an ortho hydroxy. Well, just like, and this is a new name you're now responsible for, just like hydroxyortho to carboxylic acid is called salicylic acid, this molecule is called salicylaldehyde, all one word. Salicylaldehyde. Okay. How do you get an aldehyde from CHCl3? Well, the answer, this is the reaction, the mechanism of formation, is a reaction that you were told you'd probably forget. A reaction you should have learned in the alkene section. And that is what happens to CHCl3 when you react it with hydroxide or a base. See, chlorines are electronegative. Electronegative enough to allow a small amount of equilibrium to form. And it's mainly shifted left, but there will be some deprotonation. And you will produce some carbanion, CCl3. Now this carbanion is not very stable, but it does have a good leaving group, and it can subsequently fall apart if a chloride leaves and give you Cl-. And this guy is our carbene, dichlorocarbene. Dichlorocarbene forms. Now dichlorocarbene, if you remember, has an empty 2p orbital. It's sp squared. The chlorines and the lone pair are in sp squared orbitals, but there's this empty 2p. And you were told that dichlorocarbene is both a powerful nucleophile and a powerful electrophile. It can accept electrons. In the presence of benzene, it can add. In the presence of very activated benzene, a very activated benzene. Why is it activated? Well, phenol is activating. But in base, phenol deprotonates readily. We have OH minus. We added OH minus to CH3. So we're in the presence of phenoxide. Phenoxide. So what happens? What happens is oxygen dumps its lone pair, and the electrons, pi electrons, go into the empty 2p of dichlorocarbene. So, if we have dichlorocarbene in the presence of phenoxide, the attack will go on the empty 2p orbital, and you will produce this very short-lived intermediate. We'll have an H, we'll make a bond to CCl2. It'll have a lone pair and a negative charge. We'll have a double bond O here. And we will have temporarily disrupted aromaticity. Well, you can clearly see what's going to happen. The carbanion is going to grab the H. The electrons from the bond, the H+, will move back to restore aromaticity and will restore our phenoxide. So this very quickly goes and forms CH with 2 chlorines on it. And if you look at this, we have O minus. The 2 chlorines on a benzylic carbon. And benzylic carbons are very reactive to nucleophilic substitution and when in the presence of hydroxide, which is a good nucleophile. So it's not surprising that we would have an OH minus come in and do attack. Nucleophilic substitution now takes place, and we kick out a chlorine. And so, what happens? We get our aromatic ring with our O minus. And off of the ortho position, I have an H. I have an OH, 2 lone pairs, and I have a good leaving group. The chlorine still doesn't look like an aldehyde, but we're getting closer. We have an oxygen. Now, also kicked out with Cl minus at this point. Well, we can lose another Cl minus because it is a good leaving group. This is a benzylic carbon. We would get a resonance stabilized carbocation. Two lone pairs. So there's a plus here. We've got an O minus. What's interesting, this is not just resonance stabilized around the aromatic ring, but this OH can also dump in electrons to the positive charge. And I can get this resonance structure. And once you see this resonance structure, now you begin to see where the aldehyde comes from, because this contributor is just a protonated aldehyde. And in base, remember we're in the presence of hydroxide. That proton will come off really fast. So if you like, hydroxide comes in, grabs the proton and goes off as H2O. And what you're left with, of course, is our final product. Salicylaldehyde. That's been deprotonated. And hence the second step, or the last step, step 2, which was the addition of H plus or H3O plus. And all that does is protonate to give us the salicylaldehyde. Don't know if I have room, I'll try drawing it. I'll just draw CHO for the aldehyde this time because I'm out of room. And OH. Makes my salicylaldehyde. So the Reimer-Tieman reaction utilized a carbene to make a salicylaldehyde. Carbenes were used in alkenes to make cyclopropanes. This is the second time we've seen them. Make sure you don't forget this reaction. It's very easy to think of chloroform as just as a solvent, but in this case you have to memorize that it can form dichlorocarbene. The dichlorocarbene, being a strong electrophile, activated aromatic ring with O minus on it. It attacks, you end up with this CHCl2, which subsequently undergoes nucleophilic attack by hydroxide. A series of losses of chloride lead to the formation of the aldehyde group. responsible for the Reimer-Tieman reaction. The last thing with regard to phenol chemistry that I want to consider is oxidation. Phenols tend to resist oxidation, since carbonyl formation would destroy aromaticity. However, there are molecules related to phenol, 1,2 and 1,4 dihydroxybenzenes, molecules such as these, that are called hydroquinones. This is phenol. Put another OH in the fourth position, and you produce a molecule called a hydroquinone. Okay? 1,4 hydroquinone. You can also have one, 2 hydroquinone. Now, we're going to use O in square brackets as usual to represent an oxidizing agent. You go backwards if you use a reducing agent, so that's H in square brackets. Okay. If you oxidize these, you can produce 1,4 benzoquinone, which looks like this. This is called 1,4 benzoquinone. Now when you do this oxidation, you get 2H plus and 2 electrons. In the case of 1,2 hydroquinone, oxidation will yield 1,2 benzoquinone. Now, this oxidation proceeds with very mild oxidizing agents such as silver plus and iron 3 plus. The ability of hydroquinone to get oxidized and easily oxidized by silver ions means it will reduce the silver plus to silver metal. This is the chemical basis of early black and white photography. When silver is used as the oxidizing agent, silver plus will pick up the electrons and silver will become silver metal. Now, what is interesting is that silver plus silver halide, as it's applied to paper when it's exposed to light, undergoes this reaction more easily. That is, silver halide exposed to light. Silver halide exposed to light is more easily reduced to silver metal. Than unexposed silver halide. When this activated silver halide is exposed to hydroquinone, the hydroquinone is in solution, and we call the solution the developer. So hydroquinone in the developer reduces the light-activated silver. The light-activated silver halide. So the reaction takes place. And so what you do is you take this paper that's been coated in silver chloride, you put it in a box in the dark, bring that outside, remove a lens cap, expose it to light, go back into the dark, remove the paper with the silver halide, and dip it in this developer solution, and you time it so the hydroquinone reduces light-activated silver halide, but not the silver halide that was not light-activated. You remove it from the developer, and you put it in a solution called the fixer. Unreacted. Silver halide that is still on the paper, unreacted silver halide is treated with Na2S2O3. It's treated with Na2S2O3, which is called sodium thiosulfate. This is called the fixer, so this is the fixing process. So in the fixing process, unreacted silver halide treated with sodium sulfate becomes water soluble. And is washed from the film. So it's washed away from the paper. Now, if it was left there, it eventually would have turned to silver halide too, and your entire paper would have turned black. So where the light hit, you produce dark silver metal. The silver obviously is oxidized, so it's not shiny, it's tarnished. And on the bits of paper you have these specks of silver, and on the where the light didn't activate it, you get white areas. And if you move out, the result of this is what we call a photographic negative. All we have to do is repeat the process of the negative, basically take a picture of the negative to generate a photographic positive. Well, there you have it. That's the end of another Scribblecast lecture. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening,